Hello and good afternoon. A warm welcome to Researcher's Desk. It's a great pleasure for me today to welcome David Beerling, who's published a recent study in Nature on enhanced weathering. And having had a look at that study, I thought this was something that I need to learn a lot more about. And I also feel that our community here at Researcher's Desk will hugely benefit from learning more about. David's very kindly joining us here from the UK. And David, thank you so much for being here. Welcome to Researcher's Desk. I look very much forward to listening to you. I'm going to turn my own camera off so we have a really nice recording, and I will just appear instantly if something goes wrong technically. Thank you for being with us, David. Welcome to
Great.
Researcher's Desk.
Thank you very much, Alasdair, and thank you for the invitation to talk. What I thought I'd do is just maybe take a step back and not just dive into a turgid nature paper and just give you a sort of the bigger picture about enhanced weathering and just take you through some of the work that we've been doing. Um, by way of background, I'm director of the Leverhulme Centre for Climate Change Mitigation, which is a 10-year program funded by the Leverhulme Trust in the UK to look at all aspects of enhanced weathering, from Earth systems modeling through to field trials, through to public engagement and public understanding. And so what I thought I'd do is just give you a brief intro about what is enhanced weathering, and then show you some of the modeling work we've been doing. Some of it was reported in that paper that Alasdair just referred to. And then also show you sort of connect the dots from model world to the real world and show you a little bit about what some of the field trials have been showing, how this technology works. So quick primer then on why we need carbon dioxide removal technologies. This is global emissions of carbon dioxide over the last 100 years, risen from about 8 gigatons to about 40 gigatons, just over 40 gigatons. And then if we want to kind of limit global warming to 1.5 degrees or 2 degrees, then the next 100 years it has to look something like this according to the different integrated assessment models. And you can see that as incredibly uh, formidable challenge that humanity faces. And it requires two things. First, it needs us to transition to clean energy to slow CO2 emissions from combustion of fossil fuels. But then you'll also see we need to go net negative where we take CO2 out of the atmosphere. This is legacy CO2 emissions, but also there'll be some sectors of the economy that are going to be very difficult to decarbonize, and we're going to have to compensate for that with carbon dioxide removal technologies. I should say right at the start, there's no substitute for emissions reduction. That has to be the number one thing for addressing the climate crisis. And also, not emitting it in the first place is a much better option than trying to get it back out of the atmosphere, which is difficult and expensive to do. So our work is focused on enhanced weathering. And if you don't know what it is, this is a very simple kind of cartoon schematic. It starts off with our crops growing in the fields, and you apply crushed magnesium, calcium rich silicate rocks. And then with the aid of CO2 dissolves in rainwater, so you form carbonic acid in soil waters, plus there are biological processes. And so carbonic acid plus biological processes helps break down the silicate rocks with a high surface area. This produces bicarbonate, which over time is flushed through river systems into the oceans, where it's stored on a timescale of sort of 1,000 to 10,000 years, either in dissolved form or it can be deposited as calcium carbonate in limestone or uh, shellfish. So some of the features about enhanced weathering then is that the application of rocks to croplands in this way really harnesses long-term weathering reactions between basalt and climate, which have really been stabilizing climate for tens of millions of years. If it was proved to be successful and effective, it's potentially deployable at scale because within a decade or two, because agriculture is already applying crushed rocks to the land surface. to manage soil pH. It's also compatible with other CO2 management proposals, such as, growing bioenergy crops. You could combine that with enhanced weathering. Afforestation or reforestation could be combined with enhanced weathering, and similarly with biochar. So it's got scope for moving beyond simply doing it in an agricultural setting. So back in 2018, nearly 10 years ago now, we published a sort of position paper in Nature Plants where we tried to synthesize all the different lines of evidence as they stood back in, as they stood at that time. And it made quite a splash, even though it was just sort of synthesis paper. First of all, Nature weighed in with an editorial, which called it negative thinking. We basically tried to emphasize in this paper how not only would it capture carbon, but it could also help with global food and soil security for reasons that I'll explain in a moment. And Nature weighed in with a very negative editorial saying scientists must continue to spell out to policymakers the harsh reality of what negative emissions must evolve. They were all a bit depressed that they'd missed the whole take-home message of our paper, which was really all about how you could do this and then improve soil and crop health. And then the following week, New Scientist also published an editorial on the paper where they said what's uplifting about this new idea is that it offers hope for the efficacy of geoengineering more generally. So the New Scientist editors got it, but the Nature editors didn't. So in a way, the whole point of funding these Leverhulme Trust centres has been to promote disruptive thinking. So I think we kind of tick that box with this first paper. So why do we think it could improve soil and soil health and yields? Well, we know that the weathering reactions can reverse soil acidification, and we know that intensification of agriculture using nitrogen fertilizers and phosphate fertilizers causes acidification, which limits yield. So that's one factor. We also know that most of the major food crops are silica accumulators, and that by stripping biomass from the soils over repeated harvests, you're depleting the biologically available silica pools. So adding silicate rocks reverses that trend. And similarly, by the same principles, removing biomass also removes micronutrients like phosphorus, potassium, molybdenum, iron, which can be replenished by the weathering of basalt. And generally, you get improved soil health through increased root production and addition of soil organic carbon. So these can increase crop production or yields, and increased silica can also lead to crop protection. So both of these things could potentially, in theory at least, reduce agriculture usage and costs of fertilizers and pesticides. So one of the first tasks that we set ourselves then as a centre was to try and develop better numerical tools for trying to understand what the carbon dioxide removal potential of this technology is. And back in 2015, the only estimates that we really had were those published in the IPCC report, with very large uncertainties, which were basically back of the envelope calculations. And you can see the potential. This is enhanced weathering, this central pink square, was somewhere between 2 and 4 gigatons and cost somewhere between 50 and 200. And those were global numbers, so we had little idea about how it might shape down for each individual nation. So we developed improved numerical tools and then applied it on a nation by nation basis and estimated what the potential is for different nations, which each of these postage stamps is an individual nation, for removing CO2. That was the first approach. And then the second approach was we decided to start thinking about how you dynamically couple soil weathering model with a climate model so you can do these time series of carbon dioxide removal simulations. And just those two steps took us about 8 years. And these are the four things that were involved in that. First of all, we had to develop a computationally efficient one-dimensional soil profile weathering model. The second one was we had to think about how you weather dust particles, rock dust particles. Instead of just having a single particle of known diameter, you actually had to have a a distribution of particles which is more representative of how farmers would apply it to the field and do the maths behind how that's weathered. Then we also need to understand how nitrogen fertilizers affect weathering. And we also need to constrain the availability of rock according to quarrying within any one nation. So just those four steps were kind of a journey towards relevance in understanding the CDR potential of nations. And so the paper that we published last year or 2 years ago in Nature was really about how enhanced weathering with US agriculture might deliver carbon dioxide removal and how it might contribute to the US net zero goals. And the reason that we focused on the US was really because there was a report published a couple of years ago, back in 21, where they decided what the long-term strategy for the US is for getting to net zero. And they considered all of these different CDR technologies except enhanced weathering. And so for us, I could see that was an opportunity for our centre to try and redress the balance. So anyway, we did very detailed studies where we looked at mining of rock on the east coast and mining of basalt rock on the west coast. And we looked at transport to the Corn Belt. And we did two scenarios, low and high mining capacity. So the low one is blue here, and the high one is in red. And the dashed lines represent extraction. So cumulative extraction. So the low one is about 0.2 of a gigaton by 2070, and the high one is about 0.6 of a gigaton by 2070. And then we did a sort of detailed transport analysis where we looked at how applying the rock from these sources affects carbon dioxide drawdown, net carbon dioxide drawdown. And you can see the bottom line is, over time, as you increase the availability of rock, you increase the geographical area that you can apply the rock to, the number of states you can apply the rock to. And so your carbon dioxide removal potential goes up. So you can see the blue line is the provision of rock, and then this solid blue line with the shading is carbon dioxide drawdown. And it goes up. If you extract more rock, you capture more carbon. And so by 2050, we reckoned you could get net between about a quarter and 0.4 of a gigaton of CO2 removal by 2050 using enhanced weathering. And we also did some work with colleagues in the US, Chris Reinhard in particular, Georgia Tech, where we then took the weathering products from the soil and allowed them to flow into river systems, and then did river chemistry calculations to ask how durable is that CO2 removal on its pathway from fields to the oceans, and how much would you get in terms of re-emissions of CO2 as a consequence of calcium carbonate precipitation. And it turns out to be quite low, but the leakage is about 5%. You can see this is leakage that Chris's team calculated here. So the conclusion from this study was that we thought enhanced weathering, which is currently an overlooked CDR strategy, could potentially provide 30 to 60% of US engineered CDR goals by 2050. So that was the sort of the very broadest conclusion of that study. And then, as I said in the intro, just to join the sort of modeling world to the real world, we've also set up over the last 10 years a global network of field trials where we're actually looking at the performance of this technology in the field. And what I wanted to do was just give you some snapshots of one of the sites in the US and one of the sites that we've set up in the UK. We have tropical agriculture represented in cocoa production in Brazil, oil palm production in Malaysia and Borneo, and then several sites in the UK. So in the US, then, we're working with the University of Illinois, right in the heart of the Corn Belt. And it's great because they have a working farm there. And so, again, you can spread rocks with existing machinery and have large-scale field trials. And so we have four 3.8 hectare blocks. One is with basalt and one is without basalt on a corn soy rotation, and one is with basalt and one is without basalt on the bioenergy crop miscanthus. And then each one of those large 3.8 blocks is replicated in a 0.7 hectare plot. So it's a well replicated experiment. And we've been applying basalt at the rate of about 50 tons per hectare every year for 7 years now. And as I said, it's on a maize soy rotation. And the point of this is really that maize is heavily fertilized. So and soybean is a nitrogen fixer. So you have 2 years where it's heavily fertilized and 1 year where the system recovers with a nitrogen fixing crop legume. And so just to tell you a little bit about the geochemistry behind measuring carbon dioxide removal rates. This is a very simplified, sorry, I've lost my pointer. This is a very simplified version of the weathering reaction whereby you can see there's the calcium silicate. It reacts with carbon dioxide and water that dissolve to form carbonic acid. And that weathering reaction releases carbonic acid. And you can either measure weathering by the production of bicarbonate, where you use lysimeters, which are tubes that go into the soil and you extract that soil water under vacuum. And that gives you an immediate measure of carbon dioxide removal. Or you can measure the amount of the feedstock that you've mixed in with the soil, how much of that is dissolved. And that gives you a measure of the carbon dioxide removal potential. In other words, if all of the cations that are produced by weathering are charge balanced by the formation of bicarbonate. And again, there are techniques to measure that. So one is if you measure the cation loss in the soil, that's your weathering potential. And if you measure your bicarbonate production in the soil water, that's your actual weathering rate. So this is some results then from the field trials. This is the first 4 years of the field trials in the Corn Belt of the US. And again, you can see that carbon dioxide removal potential increases over time with repeat applications of rocks going up to about 20 tons per hectare after 4 applications. And you can see there is some noise in the system there, but if you kind of bootstrap it, you can see that actually in terms of number of soil samples you need, it's somewhere around 10 to 15 before the annual rate converges at a CDR rate of about 4 tons per hectare. Now, in terms of thinking about how to improve soil pH, you can see it's quite clear on the charts here. On the left-hand side, this is soil pH. You can see that with basalt, solid squares, pH goes up. And then without basalt in the control plots, you can see that you get that typical acidification that you get with nitrogen fertilizers. So it's reverse soil acidification. You see the same pattern at 0 to at 10 to 30 deeper down the soil profile. And then we've also seen increases in yields. So this is the maize yield. So the first year we did it with maize, we saw an increase in yield. So that's the difference between the open and the filled bars. That's about a 10% increase. And then the next year with maize, it disappeared. Then we did it in soybean. There was a 16% increase in yield. And then the final one, maize there, we saw a 12% increase in yield. And for this, we're really interested in knowing, are these yield increases just due to pH or are they due to the replenishment of micronutrients as a result of the basalt weathering? So we did a liming treatment, replicated liming treatment, which just gives you the pH effect. And you can see that the basalt treatment is more than just the liming alone. So there are additional benefits from the basalt. One of the things that we've seen very consistently in the US field trials are reductions in N2O. So this is cumulative N2O emissions. These are just 4 different years, and it varies from year to year because of variations in climate. But we see a consistent reductions in N2O. And Maria Val Martin in our research team has parameterized the US community Earth systems model to try and understand what are the consequences of this for atmospheric chemistry and the feedback on aerosols. What she found is then it reduces the surface ozone concentration as a consequence of widespread application of basalt in the Corn Belt. That's both important for human health, so this has implications for avoiding premature death, and also reduces the acute exposure that affects crop health, so that can improve, that's an indirect effect on yields, and also reduces summertime PM 2.5. So these are essentially secondary organic aerosols. So there were small increases in ammonia, but no reductions in secondary organic aerosols. And so Maria figured out what would be the maize yield increases as a reduction of that surface ozone concentration. And it's about a 3% boost in yield, which across the Corn Belt is pretty significant in terms of the economic value. And soybean, which is less sensitive to ozone than maize, maybe about a 2% yield, but again, worth about 1 billion. So pretty amazing numbers, and these yield increases are indirect as a consequence of improved air quality. And just to show you a snapshot of what we've been doing in the UK, this is work funded by BBSRC and DEFRA, where we've been looking at the performance of the technology across major agricultural land uses in the UK. So we have arable crop rotation, lowland grazing, and upland grazing. And then integrated within this program, we also have public engagement, sustainability work, and process modeling. But I'm just going to give you a snapshot of what we've been finding at the field sites, just to give you a sense of it. So this is Harpenden, where we have 6 blocks. 3 are treated and 3 are controls. And we've been looking at crop rotation with soybean, wheat, and oilseed rape. Here's the surface pH. So just like in the US, surface pH goes up across the 3 harvests. You can see the surface pH here with basalt is in blue and the control is in orange. It's the 0 to 23 depth, and then the plot on the right is further down. But again, you see an increase in pH. And then we've also installed lysimeters, so we can actually measure the soil pore water chemistry. And you can see the alkalinity is higher across the 3 years. So the blue, So the blue is the basalt plots, and the open triangles is the control plots. You can see the alkalinity is higher, the base cations, the cation release from calcium release from weathering is higher, so is the magnesium, and so is the sodium. So this is really direct evidence of carbon capture happening. We've measured trace elements in the biomass of all of the 3 different crops over the 3 years. We don't see any significant increase in trace elements. We've also measured trace elements in the pore waters, and again, we don't see any increase in trace elements of the pore water, so chromium, nickel, cadmium, and so on. I think one of the things that has surprised us, we've seen a major increase in earthworm abundance consistently over 2 years that we've done the surveys, both adults and juveniles. So the earthworms really do love the basalt. Now in Northwick, we have another, which is our lowland grazing site. We have, rather than flat areas, we have strips that are 30 meters long and 10 meters wide, and then each strip gets either a control or we have 3 control and 3 treated strips. Each of these strips represents a self-contained hydrological unit with a VNOx weir at the end. So what happens is when you have a flooding event, you can collect the drainage waters off that strip and measure the chemistry of the drainage waters. So it's a really nice system for understanding the behavior of enhanced weathering. And so this is pH values of some of the drainage waters. Again, you can see the pH is higher in the basalt treated strips on the left. So as before, the blue triangles are treated and the open orange triangles are controls. So it's always high. So that's telling us weathering is going on. And then again, you can see these plots on the right here, 2024, the pH is always higher in the rock dust strips, and March 2024. Same as before, we've been measuring the alkalinity productions. This is the bicarbonate production. You can see it's always higher in the in the treated plots compared to the controls. And the same in February 24, and that should be March 24, and the DIC, sorry, dissolved inorganic carbon. So these plots are giving us a clear demonstration of increased carbon capture over time. And as with the pore waters at Harpenden, we also measure trace metals coming off, and they're usually lower, certainly not higher. And so this gives us a measure, both this data and the data from Harpenden and the US all support enhanced weathering as a safe technology. And then we can also calculate carbon dioxide removal potential by looking at how much of the feedstock has undergone dissolution. And you can see that both of the Harpenden, lowland grazing, and the arable are similar in terms of their trajectory. And then we have an upland site in Plinlimmon, which gets half the application rate, and that's also showing nice increases in carbon dioxide removal rates. And you can use these sorts of data to benchmark models. So if we know what the average rate of CO2 removal is on arable land, you could multiply it by all the arable land in the UK, and that gives you a maximum amount of gross CDR potential for enhanced weathering in the UK. And then you kind of do a back of the envelope calculation for emissions due to mining, grinding, and spreading, and you end up with a net CDR rate of about 40 to 50 million tons per year. So this is absolute maximum value. And you can do the same calculation for pasture, and it's about 40. Then you can say, well, okay, how does that compare with models? Well, models suggest somewhere between 60 and 30, and the field trials maximum somewhere between 40 and 50. So the models are not a million miles out. And in terms of thinking about how it could help the UK deliver net zero, it's maybe 20% of the UK government's target. So again, it's got potential. And just finally, then to say, in the last 3 or 4 years, there's now been this kind of global commercial ecosystem that's sprung up, where there's now like 20 or 25 enhanced weathering companies doing enhanced weathering all around the world. So Mexico, Brazil, India, China, Australia, you name it. It's become a kind of global multi-million dollar industry. They've raised probably something like $500 million, 300, $400 million. And this does kind of raise the questions. There are questions about how you do rigorous quantification of monitoring, reporting, and verification of carbon dioxide removal. And what's the level of evidence you need in order to be able to sell carbon credits on the carbon market, the voluntary carbon market. And so there is a question about, has commercialization run ahead of the science? And there's something about this combination of carbon dioxide removal plus food security, which seems to be like catnip for venture capitalist investors. And just to finish with then, I'll just say I think what I like about enhanced weathering is really that it exploits what human societies have known for decades, which is the foothills of volcanoes, where you have weathered volcanic rock, are incredibly fertile lands, and this is the foothills of Mount Vesuvius in Italy, being very actively farmed because they are highly productive soils. And that's it. I've got many thank yous. Lots of people have contributed to the field trials, to the geochemistry, to the earth system science. But I hope that gives you a kind of overview of some of the things that we've been doing over the last 10 years. Thank you.
David, thank you so much for an absolutely superb presentation, super pedagogic. Thank you very much indeed.